Welcome to Unit 6, Stoichiometry. I'm so excited. This might be the unit that you have looked forward to the least, and I just want to set your mind at ease. Okay, I feel like people get scared of the math and chemistry, but all this is fancy algebra, okay? We're going to give algebra meaning in the context of a chemical reaction, but it's truly just plugging in a process and walking through the same process every single time. And I'm going to teach you exactly how to do that. So before we can really learn what true stoichiometry is, we need to know what the mole is. So Concept 1 notes today, we're going to meet the mole and we're going to learn all about what I mean about the term mole. And I don't mean this little guy that you see in the ground. I mean the mole as in chemistry, which is abbreviated as a unit as MOL. So think of this as like, you can write out grams, grams, or you can just abbreviate it with a little g. So this mole without the E is just the abbreviation, like the unit for the mole. And the mole is just a unit of measurement, and we use it to measure the amount of a substance. But the reason that a mole is so helpful is that it's used for measuring large amounts of really tiny things. And that's what we need, because when we're talking about atoms are so tiny, and every single 10 grams of some sort of substance has so many billions of, atoms in it. And so that's why we need this mole, or else we would constantly be using scientific notation to try to wrap our minds around these giant and tiny numbers. And so the mole helps us get these values into something that's a lot easier to work with and understand. So you should be very grateful for the mole, because what one mole represents, it represents this much of something. Okay, I can't even say that number. That's how big it is. In scientific notation, we kind of usually tend to narrow it down to 6.022 times 10 to the 23rd power. That's how many of something you have if you have 1 mole of it. And this number specifically is known as Avogadro's number. And it just, again, it represents the number of particles in exactly 1 mole of a substance. So if we're looking at an element, it would be the number of atoms in it. If we're looking at compound, we're measuring, the number of molecules in it, that kind of thing. And I have a reference sheet for you that I will give every student in my class. You can use these all the time and on my tests. And it has a lot of things that will help you. It has some reminders about sig figs, because we're going to need to kind of refresh on significant figures in this unit, just because, again, we're going to be doing a lot of calculations. So sig figs help you know how to round those numbers. But it also has this number, and it kind of has it written out for all the different things it can mean and that you can reference, because we're going to be using these as conversion factors, which we're going to refresh on in a minute. Okay, so like I said, if you have 1 mole of gold, that means you have 6.022 times 10 to the 23rd particles of it, or atoms of it, you could say. So let's do an example of how we could actually use this number in a calculation. Okay, this is going to be like one of the simplest types of calculations we could do. So let's say you have 4.0 moles of helium. How many atoms of it do you have? Okay, so we're going from moles to atoms. So we know that we have 4.0 moles of helium. We don't know how many atoms we have. So just like we did all the way back in Unit 1, Introduction to Chemistry, when I taught you dimensional analysis, and we learned how to convert from kilograms to pounds and, liters to fluid ounces. We're going to do that exact same thing. We're just going to be using chemistry units like moles and atoms, as opposed to volume units like you were using before. Okay, so we kind of draw our picket fence, and then if you remember, we'll review conversion factors in a second, but we write conversion factors here, which are equivalent values of 1, so things that equal 1. And we always want the units to be opposite of each other so that they will cancel out. Because remember, this is basically like multiplying fractions, but fractions are scary, so we're going to draw it like a fence instead. So we know that there are 6.022 times 10 to the 23rd atoms in 1 mole. So 1 mole is the same as 6.022 times 10 to the 23rd atoms, and vice versa. So we're going to use that here as a conversion factor, but we want the units to be opposite. So we're going to put that 1 mole down here so that it will be opposite of the moles of helium. And that is equal to 6.022 times 10 to the 23rd atoms. Now, these again will cancel out, and then I'm left with what I'm looking for, which is atoms. Now we just multiply across the top. So 4.0 times 6.022 times 10 to the 23rd, and we get this number. And then we multiply across the bottom, which is just 1. and then we divide. And that's how we get our answer, which is that there are 2.4 times 10 to the 24 atoms of helium. And I knew to round this to two significant figures because we started with two significant figures. Now, if you're watching this and you have a teacher, that's not me, your teacher may not worry about sig figs. They may care a lot more about sig figs than I do. I kind of fall in the middle. I want you to be reasonable and do your best to do sig figs. If you just write a number that has like 18 decimal places, like I'm going to take off for that, but I'm not going to be, crazy about how perfectly you do your sig figs in my class. Your teacher may feel differently about this. Okay, so I want you to try this. I want you to figure out how many atoms are in 7.1 moles of silver. And then let's go the opposite direction. If you have 6.25 times 10 to the 21st atoms of lithium, how many moles of lithium do you have? Okay, so follow that same process that we've done. I'm not going to show you the answers because I want you to try this on your own and we'll go over it in class. Again, you need to have a periodic table in front of you at all times this unit, and you need a calculator at all times. And then really, I think you should have that reference sheet too, just so you can have it to help you and serve you there. Okay, so those are your three things, but you got to have those at all times. Now, let's keep trucking along for the sake of the video. Let's talk about molar mass. This is something that's measured in grams per mole, but it basically tells you the mass of 1 mole of a pure substance. Now, here is what is nice about molar mass. It is the same number as atomic mass, which is what you look up on the table. It just has a different meaning. Okay, so if you look up carbon, you see 12.01. The molar mass of carbon is 12.01 grams per mole. Look at oxygen, 16.00. The molar mass of oxygen is 16.00 grams per mole. So these molar masses, you can look them up on the periodic table for an element, which is awesome. Now, how is it different from atomic mass? Atomic mass is measuring the mass of one atom in AMUs, while molar mass is the mass of 1 mole of particles in grams per mole. So it's just using different units here. AMUs, like you may see in other things that you look at, that you see the word, or excuse me, sorry, I got distracted. The letter just U can be used now instead of AMU. But again, for our purposes, we're not going to be using AMUs. We're just going to be looking up molar masses and using grams per mole from now on. Okay, so don't even really worry about atomic mass anymore. All right, for our purposes. Now let's talk about those conversion factors, which I promised you we would review. Molar mass can also be used as a conversion factor. So remember, conversion factor is a ratio of equivalent values, meaning that they equal 1. So we talked about how like 60 seconds is the same thing as 1 minute. So 60 seconds equals 1 minute. So you can write that as a conversion factor. We can do that with molar mass too. So looking at like aluminum, the molar mass of aluminum is 26.98 grams per mole of aluminum. So what that means is 26.98 grams of aluminum is the same thing as 1 mole of aluminum. Remember, this is our abbreviation for therefore. What that means is we can write this two ways. We could write it as 26.98 grams of Al over 1 mole of Al, or we could write it as 1 mole of Al over 26.98 grams of Al. Either way, these are equal to 1, and they are going to be useful as conversion factors. Okay, so lots of conversion factors coming this unit. Another thing I wanted to remind you about that I introduced to you back in Unit 1 is this idea of radar. So chemistry, all we're doing in chemistry is problem solving. Okay, that's it. Like I said, fancy algebra. You are totally capable of doing this. I swear like 90% of this is just your confidence in yourself that you can do this. And then 10% is like actual skill. Okay, so I just need you to believe that you can do this. And I think something that really helps me and has helped my students in the past is this idea of radar. It's a method that helps you approach any problem and figure out how to get started and what to do. Okay, so what radar stands for is read, analyze, diagnose, assess, and reflect. So basically, when you get to a problem, the first thing you should do is read it and think, okay, like what are we looking for? What's this asking me? You can, if a question isn't already bolding like what you're looking for, like circle it, underline, mark what we're looking for as you're reading. Be an active reader. Okay. The second thing you do in radar is you analyze and you think, what is given to me? What did they tell me here? And you label things that you know and things that you don't know, okay? So if I don't know something, but I think I need to know it, I would label it with a question mark. If I know something, I would label what it is. Like if I know the molar mass of nitrogen, I would write that nitrogen's molar mass is 14.01 grams per mole. Okay, so this is where we're just going to organize our information, what we have and where we're going. Then D stands for diagnose. This is kind of where you make your plan going forward. So you may write all this stuff down in A and realize like, okay, I'm trying to get from like moles to grams, then I'm going to need the molar mass to get there. And so you may know like, okay, I need to find the molar mass first, look it up on the periodic table or whatever, before I can move on to the next step. Okay, that's what the diagnosing is. Assessing is where you actually solve it. You plug things in and you solve. And then reflecting is where you go back. And I also, you could think of the R as review. Go back and review. Does this make sense? Is this reasonable? Did I find what I was originally looking for from the beginning? And then the other thing I will say with the reflecting or the reviewing is I really want to encourage you anytime you finish, a worksheet of practice problems or a test, go back and at the very least, if you don't have time to like redo every problem and check them, go back and at least go through to your last step where you're assessing and type the numbers in your calculator again and just make sure you punched them in your calculator right. I cannot tell you how many times a student will have done like all the work and they just like mistype it in the calculator and they get the wrong final answer. And that is why it's so important to show all your work, because if it's like a 6-point problem and you did everything right, you just get the final answer wrong, that tells me you know what you're doing. You just like were working too fast and typed in the calculator wrong. You can still get 5 out of 6 points for that. Okay, so it's really important that we go back and we double check our work and we reflect on it, making sure it makes sense. Okay, so let's talk about molar mass in terms of just an element, and then we'll talk about molar mass in terms of compounds. Okay, so example, if you have 3.50 moles of gold, how many grams do you have of it? Okay, so we're going from moles to grams. Okay, that's what we're analyzing, we're reading, we're figuring out what are we doing? We're looking, we have moles, we need to find grams. Okay, so we know 3.50 moles of AU. To get to grams, I'm going to need that molar mass of grams to moles. And if you remember, we can look that up on the periodic table. So if you go and look at gold, which is AU, it's 196.97 grams per mole. Now you just need to figure out how you write it in here. Well, we want the units to be opposite. So we'll put 1 mole on the bottom and we'll put the 196.97 grams of AU on the top. That allows those to cancel out. Now I just multiply across the top, multiply across the bottom, and then divide. And we get our final answer. Now, you may be saying, why did you go from 689 to 689.40? Well, we started with 3 sig figs, so I wrote the answer in 3 sig figs. I'm going to be consistent with sig figs on my end, but again, I'm going to give you all some grace with that on your end. Okay, let's do another example. The other direction. Let's say you perform a chemical reaction and you produce 12.6 grams of aluminum. How many moles of aluminum did you make? Okay, so analyze. What do we know? What do we not know? We know grams and we want moles. That's our plan. So we know 12.6 grams of aluminum. We need to get to moles, which diagnosing means we got to find the molar mass. So look at your periodic table, look at aluminum. It's 26.98. Now, grams is on top here, so we want grams to be on the bottom here. So we're going to put that 26.98 grams of aluminum, and that's equal to 1 mole of aluminum, which is why we're able to do this, because it's a conversion factor. These units in grams will cancel out and we're left with moles, which is what we're looking for. Now we just need to assess it. So we need to actually like punch this in the calculator. So 12.6 times 1 mole would give me 12.6 moles. On the bottom, all I have is 26.98, so that goes down there. And then remember, this is a fraction, so now we just plug it in and divide. 12.6 divided by 26.98. And I get 0.467 moles of aluminum. So that's 3 sig figs. Remember that a leading 0 doesn't count for anything. We started with 3. Okay, so now I want you to practice this on your own. Here are a couple practice problems for you that give you some examples of the types of things you will see with this. And then we'll go over those. And then in class, we're going to do some more practice with just this. We're going to divide this up. We're going to chunk this up over several days so it's not overwhelming. So I really recommend not watching this video all at once because it's going to feel very overwhelming. But if you actually follow the pace that we're going to do in class where we like learn, take some notes for a little bit, then we practice for a little bit, take a break, come back, and I think it'll feel a lot more manageable. Now, let's keep going there for the video. So that's just, so far I've only been having you look at like calcium or aluminum or oxygen, but obviously sometimes we're going to be looking at compounds. We're going to look at sodium chloride. We're going to look at carbon dioxide. We need to find the molar mass of those as well. And if you look at your periodic table, there's no carbon dioxide on the periodic table, but we can use the periodic table to find the molar mass of a compound. Now, before we do that though, I need to give you a new definition, and this is called formula mass. This is just the sum of those average atomic masses on the periodic table of a compound's element. It's measured in AMU, but this is the same thing numerically. Just like atomic mass is the same thing as the molar of one element is the same thing as the molar mass of that one element. Formula mass is the same thing. We're just looking at the mass of the whole formula, but we're just going to be using grams per mole. We're never going to really use this unit, but I know this is like a term you're supposed to learn, so that's why I'm telling you that, okay? But all we're just doing is the sum. We're just going to add them up. That's literally it, okay? So find the molar mass of water, H2O. Okay, what do we know? Remember, that's what we always do first after we read. We analyze. What do we know? Well, we know the molar mass of hydrogen from the periodic table. It's 1.008 grams per mole. And we can look on the periodic table and see that oxygen is 16.00 grams per mole. But we don't know the molar mass of water as a whole, but we can figure it out. So I always like to have all of the things I know and don't know on one side. Then I like to draw a line just to separate it visually for myself. And then I do all the work on this side. Okay, so let's find the molar mass of water. Well, in water, there are 2 hydrogens and 1 oxygen. So I always write it out this way because I have to do 2 times the molar mass of of hydrogen to account for the fact that there's 2 hydrogens, and then 1 times 16. Okay, so 2 times 1.008 gives me 2.016. 1 times 16 just gives me the 16. And then I can just add those, and I get 18.02 grams per mole. Now, in terms of rounding, just a little reminder with sig figs, when you're adding or subtracting, we never go more specific than like the least amount of decimal places of the other one. And so since there's 2 on this one, we'll do 2 here. Okay, so this is one of those things like you just need to get started doing it. So I want you to practice doing this with sodium chloride, magnesium hydroxide, and then potassium chlorate. You might be thinking, wait, you didn't give me the chemical formula. Y'all, there's so much overlap with this unit in our last 2 on chemical bonds and chemical reactions. You have got to remember all of our naming rules. And I will give you a backup reference sheet from Unit 4 if you want it to help you. I'm fine to do that so you can remember the naming rules and all of that. I don't want that to hinder you, but I'm going to start intermixing some of this with our practice where I give you the chemical formula, first where I give you the name, and now the first thing you need to do in this one is get the formula so that then you can find the molar mass of the compound, okay? Now, before we practice this on like a practice handout, I want to teach you one more thing about what we can do with molar mass of compounds. So I can now, just like I did before with one element, same exact thing, we're just looking at a compound. I can say, hey, I've got 2.50 moles of lithium fluoride. What's its mass? And you convert that moles to grams. You just have to get the molar mass of the compound first. So it just makes it a 2-step problem. Okay, so we just read it. Let's analyze. What do we know? We know 2.50 moles of lithium fluoride. What do we want to know? We want to know the grams of lithium fluoride. We don't know how many grams there are. Well, let's diagnose. What do we need to get there? Well, to get from grams to moles, we're always going to need molar mass. So we need to find the molar mass of lithium fluoride first to get started. Okay? Again, you don't have to do this, but I like to draw a line to separate, kind of all my background stuff. Now let's solve. Let's find the molar mass of lithium fluoride. So I need to add the molar mass of 1 lithium and 1 fluoride. Fluorine, excuse me. Now this is a little bit redundant. Like you probably don't need to write this out every time with the 1. I'm just doing it to help you. Like there's one of these and one of these in lithium fluoride. Okay, so 1 times 6.94 is just 6.94. 1 times 19.00 is just 19.00. Then I can add those. Okay, I now have the molar mass of lithium fluoride, 25.94 grams per mole. I still need to know the mass of lithium fluoride. Now, if I was writing this on notebook paper, I would draw another line and then keep going to the right. So it would all be organized that way. But for the sake of the screen, I don't have that room. So I'm going to have to bring it down here. Okay, so now we've got our 2.50 moles of lithium fluoride. Now we're going to do a conversion. Okay, anytime you see that picket fence, okay, we're doing a conversion here. That's all we're doing is converting the units. That's literally it. Okay, so we're going to use molar mass. Since moles is on the top, I need moles on the bottom. So the 1 mole goes on the bottom. The 25.94 grams of lithium fluoride goes on top. Those will cancel out, leaving me with what I'm looking for, which I always like to check before I get started. And then now I multiply across the top, and I get 64.9 grams of lithium fluoride, and then I get 1 on the bottom. Divide by 1 just gives you 64.9 grams of lithium fluoride there. Okay, now let's just go the other direction. How many moles are in 125 grams of potassium permanganate? Okay, so we ask ourselves, what do we know? We know 125 grams of potassium permanganate. What do we not know? We do not know the moles of that. All right, let's diagnose. Well, what do we need to know whenever we're going grams to molar, moles to gram? We have to know the molar mass. We cannot look Km and O4 on the periodic table up, but we can look up K and Mn and O and then, sum it all up. So we'll need to find the molar mass first. Okay, so let's do that. So there's one potassium, so that's 1 times 39.10, which this number again, all I did was look it up on the periodic table. I'm going to add that to 1 manganese, which if you look up on the periodic table, that's 54.94. And then I've got oxygen. There's 4 oxygens here, and oxygen has a molar mass of 16.00. Again, looked up on the periodic table. So I'm going to write that all out. Now, 1 times that is just the same thing. 1 times that's the same. But then 4 times 16 gives me that 64. And then I can add those all up, and I get 158.04 grams per mole. I'm not done, though, because I wanted to know the moles. Now we do our conversion and get to our picket fence. Now we have everything we need to do a conversion. So I start with 125 grams. I draw my picket fence. Okay, the units have to be opposite, so I'm going to put the 158.04 grams on the bottom, the 1 mole on top, multiply across the top, multiply across the bottom, and then now I divide. And that's where we get our answer of 0.791 moles of potassium permanganate. Okay, you try this. And the first 2 are like what we just did. The last one's going to take it 1 step further, okay? I'm going to ask you for molecules. So you'll have to go grams to moles and then moles to molecules. Remember, you can always go moles to molecules, moles to particles, moles to atoms, because you know Avogadro's number. That's on your reference sheet too. So try this. This just gives you an extra step in the conversion factor part, and then we will go over it. And then we will practice this a ton in class together. Now, I think 2 more things I need to teach you in this concept before we kind of wrap it up with Meet the Mole. And then first is percent composition. So we're going to do a little inquiry lab activity that's going to make this make a lot more sense and be a lot of fun. So we're going to pause and do that in class now, but for the sake of the video, just kind of keep going. I know this is a long video. I would literally never lecture to you this long in one sitting, but it's just got to do it for the video. Now let's learn about percent composition. This is just a percentage based on mass of each element in a compound. And it follows the same equation every time. It's the percent of an element in a compound, the percent composition in orange is equal to the mass of an element in 1 mole of the compound divided by the molar mass times 100. So it's just, anytime you're doing a percent, it's just part over whole times 100. So that's all we're doing. So we just need to know the molar mass of a compound in order to find this, okay? So this is why this connects to what we were just doing. Let's do a couple of examples so that it'll make more sense. So let's say I first just asked you, find the percent composition of CO2. Okay, so we're gonna do this by mass. So what am I looking for? I'm looking for percent composition. To do percent composition, I always need to know the molar masses of the formula. So those just go hand in hand, okay? So first, let's find that molar mass. There's 1 carbon, which I look it up on the periodic table. Carbon has a molar mass of 12.01 grams per mole. And there's 2 oxygens, so 2 times 16. So I get the molar mass of carbon dioxide to be 44.01 grams per mole. Now I'm not done because I need to know the percent composition. So now we just plug it into that formula. Okay, so first let's find out what percent of carbon dioxide by mass is carbon. Well, part over whole. So the mass of carbon in 1 mole is 12.01 over the total molar mass, which is just 44.01, and then I'm going to do times 100, and I get 27.29% carbon. Now, for oxygen, I have to take into account that there's 2 of them. So I have to do 2 times the 16 grams of oxygen divided by the total, and I get 72.71% oxygen. Now, because there's only 2 elements in this, you could always just do 100 minus this to find the other, but I just wanted to write it all out so you could see it. Okay, so that's one way we can also kind of take molar mass and do another type of calculation with it. The other way you might see percent composition is a little bit trickier, okay, and it's like this. Magnesium hydroxide is 54.87% oxygen by mass. How many grams of oxygen then would you expect to see in 225 grams of the compound? So you're basically saying this is how much oxygen by mass is in there, so how much oxygen would I expect to see if I had this much of the compound? So we know that 54.87% of magnesium hydroxide is oxygen. We know that we have this much magnesium hydroxide. We want to know how much of that is oxygen then. So all we need to do, I'm going to diagnose this, is we need to find out what is 54.87% of 225 grams. That's all we're doing, okay? So part over whole, so that's the part of the percent over the total 100, it's got to be equal to however many grams of oxygen there are over 225. So anytime you have a percent like this, you can do kind of a crisscross calculation. So I can do 100 times this and 225 times this. So 225 times 54.87 gives me 12345.75, and that's equal to 100 times grams of oxygen. Now, to get grams of oxygen by itself, I just need to divide by 100 on both sides. And that's where I get that there are 123.4 grams of oxygen in 225 grams of the compound. Okay, so let's practice this. First one is just like the first example we did. The second one is just like the second example. Try that, and then we're going to do some more practice in class. Again, this is so much easier if you do it in chunks. If you're trying to learn this all at once, it's going to feel overwhelming, okay? All right, let's finish up with the last thing that we need to learn in this concept, and that's how you can figure out chemical formulas. Now, you might be thinking, like, Rebecca, we know, like, you tell me sodium hydroxide, and I write the ions, and I crisscross the charges, and that's how I get it out. Okay, well, sometimes you might get a situation like this, where someone tells you, hey, you've got 110 grams of an unknown compound. All we know is that 18.8% of it is sodium, 29.0% is chlorine, and 52.2% is oxygen. What's the chemical formula? How do I figure that out? Okay, now here's what you basically got to do. First, you got to figure out how many grams you have of each element. Then determine how many moles you have of each element. And then you compare the ratio of moles to determine the ratio of atoms in the compound. And so we're going to do that. We're going to do this by dividing the mole numbers by the smallest one. Okay? Sounds more overwhelming than it is. Let's walk through this together. Okay? So I just kind of wrote that example a lot smaller here so we'd have more room to work on walking through the steps. Now, one thing I want to tell you really quickly is if they don't tell you this mass, you can just use 100 and figure out like, okay, what's 18.8% of 100? 18.8. What's 29% of 100? 29. Like you can kind of do it that way. We'll practice that too. But since they gave us mass, we're going to use it. So to figure out how many grams of sodium are in this compound, we need to find 18.8% of 110 grams. So we're going to do exactly what we were just doing. Do kind of like the write it out, crisscross, and you figure that there's 20.7 grams of sodium. Same thing. Let's figure out what's 29% of 110. It's 31.9 grams of chlorine. And then what's 52.2% of oxygen? 57.4 grams of oxygen. Okay? So that was our first step. We figured out how many grams there are. Now we need to know how many moles there are. Well, you know how to convert grams to moles. How do we do that? With molar mass, which these are just individual elements. So you can just look them up on the periodic table. Okay, so sodium is 22.99 grams in 1 mole. Multiply across, I got 0.900 moles of sodium here. Chlorine, look it up, 35.45 grams per mole. Multiply across and divide, I get 0.900 moles of chlorine. All right, 57.4 grams of oxygen. Plug it in from the periodic table, divide, I get 3.59 moles of oxygen. Now, that was step 2. Now we do step 3. Compare the ratio to determine, compare the amount of moles basically to determine the ratio. Okay, so take 0.900 moles of sodium and divide it by the lowest number here, which is 0.900, and I get 1 mole of sodium. Now let's look at chlorine. Same thing, 0.900 moles of chlorine divided by the lowest number. I get 1 mole of chlorine. Now let's look at 3.59 moles of oxygen. We're dividing by the lowest number, which is 0.900. So we're dividing all of these by the same number, and we get 4 moles of oxygen. So I take all of these together, and that's how I figure out the chemical formula. It's 1 mole of sodium to 1 mole of chlorine to 4 moles of oxygen. So it's NaClO4. That's how we can use this percent composition to determine the chemical formula of a substance. Now, the last thing we have to add on here, if you're like, wow, this is too much. I know it's a lot, but I promise with practice, you can do this. I promise you can do this. There's a difference between the empirical formula and the molecular formula. So empirical formula is the symbols of elements and subscripts written to represent the lowest whole number mole ratio of atoms in a compound. So that's what we just did. You just did this. You found the empirical formula. Now, the molecular formula is the actual formula for the compound, which isn't necessarily always reduced to the lowest whole number ratio. Okay, so for example, the empirical formula for a compound could be BH3, but the molecular formula is B2H6. So see how that's just 2 times this? So that's where like the empirical is the reduced version, the simplest version, the molecular is the actual version. Now, for ionic compounds, these are always the same. Because remember, ionic compounds are already just representing a ratio in a crystal lattice. Okay, so it's like sodium chloride is representing that there's 1 sodium for every 1 chlorine in this giant crystal structure. Okay, remember in covalent compounds and molecular compounds, it's the actual number of like carbon dioxide is 1 carbon bonded to 2 oxygens, period. Okay, so that's where you're going to see this play out differently is with covalent compounds. So let me show you how to figure that out and how we move from there. So basically, to figure out a molecular formula, you got to find the molar mass of the empirical. So this is just taking it one next step. You just did what you did. Now we're going to find its molar mass and then compare it to the actual molar mass given for the compound. So that's going to have to be given to you. If it's the same, then the molecular formula equals the empirical formula. And if it's different, then you'll divide by the smallest number, and that's going to give you your multiplication factor. Then you can multiply the whole thing by that number, and you'll get your molecular formula. Okay? Sounds more complicated than it is. Let's put it into action with a couple of examples. So first, let's say find the molecular formula for CH2 if it has a given molar mass of 42 grams per mole. So first we said find the molar mass of the empirical formula. So find the molar mass of this. Okay, well, carbon is 12.01, hydrogen is 1.008. We don't know CH2's molar mass, but we can find it. So 1 times 12.01 plus 2 times 1.008, and we get 14.026 grams per mole. Okay, that's step 1. We found its molar mass. Now we just need to compare this to this. So first of all, look at those. Are 42 and 14.026 the same? No. So that means your empirical and your molecular formulas are different. This is a reduced version of the actual formula. So now we do, if it's different, just divide by the smallest number. So take that 42 grams, divide it by 14.026, and you should get 3. So what it's telling you is that the molecular formula is 3 times bigger than this. So all that means is that you're going to take 3 times CH2, distribute that, you should get C3H6 is the molecular formula for this, and CH2 is the empirical. Okay, let's do another example. Okay, now let's say it says find the molecular formula for CH2 if the given molar mass is 70. So that's the only difference here. We're going from 42 to 70, okay? So you'd still do the same process, find the molar mass, which we already did, which is why I didn't rewrite all of that. That threw me off for a second. I was like, what did I do? I just didn't retype it all. So again, you just move on to the second step. Take 70 divided by 14.026. You get 5. So therefore, 5 times CH2 gives you C5H10. That's the molecular formula. So that's all we're doing here. And we are going to practice this, okay? You can do this, okay? If there's anything you hear me say during this is you can do this. You are your worst enemy here. If you give up on yourself, then you will give up on this. But I promise you, hundreds of students have been learned to do this. In my classroom, millions of students across the world have learned to do this. You can 100% do this. Let's just follow the steps and work through it together. And if you need extra help, come in for it. I would love, love, love to help you work through all of this, okay? But this is already getting long, so let's cut this off and get to practicing.